Hello, welcome to your lesson on tangent and normal lines. This is kind of a big idea in differential calculus, so let's get started. First of all, let's recap a couple of things we talked about in our previous lesson. We began by talking about gradients or slopes, and we said, hey, when we have a linear function or linear equation, the slope is constant, it's always the same. So when we say find the slope of this line, we can just say the slope is the same everywhere on it. However, we have taken a step forward in calculus. We have said, hey, what about if we have curves? And along curves, there is no one set slope. The slope actually changes as you follow the curve. And the slope can be represented by a series of tangent lines. You can see a tangent line here, here, and here. And a tangent line represents the slope at that particular moment in time. So here we can see no slope down here, or here at this point right here, we can see a pretty steep positive slope, for example, and here a negative slope. So let's go to Desmos where I can just reiterate this idea. Okay, welcome to Desmos, where we have a curve, a parabola, red curve, and you can see the slope along the curve changes as you follow the parabola. And here we have this point here, marked on here. And at that point, we drew a tangent line. That tangent line represents the slope at that point. So now what happens when I move that point along the curve? The slope changes. Look, the slope is becoming less steep. And it's represented by this tangent line, which is becoming less steep as well. What's going to happen when the slope reaches this vertex here? Okay, let's see. When you get there, at the vertex, there is no slope. Look, the slope, the tangent created a perfectly horizontal line with slope of 0. That means there's no slope at that point. And then after that, oh, look at that. The slope is now positive, getting steeper, steeper, steeper. So again, the tangent line represents the slope of the curve, and the slope is different at every point because the slope changes. All right, let's go back in here and go forward. So here we have a parabola, a basic parabola, x squared. If we take what is called the derivative, represented like this, of x squared, it becomes 2x. The derivative is an important function. The derivative, however, a common mistake students make when first starting with calculus is they say, oh, the derivative, oh, that's the equation of the tangent line. No, the derivative is not the tangent line. The derivative is the slope of the tangent line, okay? So don't confuse it. This is not the equation of the tangent line. This is the slope of the tangent line. So for example, if we went to the point -2, x is -2, and we put that in here, we get a value of -4. That means when x equals -2, right here, the slope of that tangent line, or the slope of the curve at that point, is -4. And we can confirm it here. All right, then if we go to point x equals 1 and we put 1 in here, we get a value of 2. So now we're saying that when x equals 1 right there, the slope at that point, or the slope of the tangent line, is 2. And we can confirm that here. All right, important point. Let's go on. Today's goal in this lesson is to create equations for tangent lines. So now we know how to find the slope of a tangent line, but how do we create the equation of that tangent line? And we will also move forward from there and create equations of what are called normal lines. Let's keep going. Okay, look at this amazing place. You might want to pause and just stare at this for 5 minutes. How beautiful is that? Where are we? Well, this is a place called Meteora in Greece. A beautiful place with these, I guess, limestone karst mountains, and on top these old monasteries were built where the monks knew they could not be attacked and they could meditate in peace. Oh my, it's like heaven. Look at that, amazing. So I've been to this place, and we went to 5 or 6 of these monasteries. It's just incredible, it really is. And now let's do a problem related to this. So we have the side of a hill can be modeled by this function. Okay, so imagine this hill. Now, there is a monastery at the top of the hill, there it is, which could be an interesting tourist attraction for sure. So it is decided to build a funicular railway. If you don't know what that is, it's one of these kinds of railways. To reach to almost the top of the hill, the funicular can be modeled by a tangent to the curve where x equals 50. Okay, part A, sketch the graph. Put this on your calculator. graph it on your calculator, change the window so you can see the full graph. Okay, you should have something like this. It's appearing here. Alright, so that's going to represent our hill, and it should be this parabola. Now, there's the monastery on top, of course. Okay, B, find the derivative of this function. Okay, based on the power rule we learned last class or last lesson, there's the derivative. Drop that exponent, multiply, and here when we have this x, it just stays as the coefficient. Alright, part C. Find the gradient of the tangent at the point where x equals 50. And remember, when we put x values into the derivative, we are finding the slope or gradient. So put 50 right in there. Let's find the gradient of the tangent line when x equals 50. Alright, so 50 goes into the derivative, and we get 1.4. That means the slope of the tangent line is 1.4. Part D. Find f of x when x equals 50. So now this is not the gradient, and this is not the derivative anymore. This is the original function. So it says, what is the original function equal to when x equals 50? So put that 50 back in the original. Alright, and what we get there is 120. And that means the coordinate on the original graph is when x is 50, y is 120. And we can see that here, when x is 50, y is 120. So we've just basically found a coordinate. Okay, last step. Hence, find the equation of the tangent. So now we can find the equation of the tangent line at x equals 50. Okay, we know the slope of the tangent line because that's what we use the derivative for. The derivative gives us the slope. So we found the slope at x equals 50. It is this. And now we know this coordinate because we found it by putting x 50 into the original function. So we know a slope and we know a point. When we know those two things, we can find an equation of a line. And a tangent line has an equation like this, y equals mx plus c. So we're going to replace y with 120. We're going to replace x with 50, and then we're going to put the slope in here for m. This allows us to solve for c. What is it? Okay, solve for c, and that gives us now our equation of the tangent line. Again, the steps were find the derivative, put the x value into the derivative to get the slope, then put the x value into the original function to get the coordinate, and then use the slope and coordinate to create the equation. Here is that tangent line. Here's that point 50, 120. Here is that tangent line, and that tangent line, according to this problem, represents the funicular rail. And notice this line works. It matches what we have here. When we look at the equation of a line, this last number is your y-intercept. Follow this tangent line, y-intercept of 50 right here. Alright, now let's talk about what a normal line is. A tangent line we've been talking about. It's this kind of line. It hits a curve at one point. A normal line is a line that is what to the tangent line? What's the word that describes this relationship between the blue and the green line? Well, I hope you came up with perpendicular. Those two lines are perpendicular to one another. So that is what a normal line is. It's perpendicular to a tangent at that same location right here, that same point. Okay, here's kind of an interesting application of normal and tangent lines. So imagine you have a cyclist and they're going around a track. This doesn't have to be a cyclist. It can be a car or anything that's riding around on a sloped surface. There's some force. If you've learned anything in physics like this, you can see here, for example, here is the tangent, here's that track or the wheel, here's the tangent, and here's the normal. The normal line represents the force of the bicyclist or the car or whatever's going on this track, the force that keeps it connected to the road. If there was no force along this perpendicular line, the bicycle or car would skid off to the side. Alright, so that's a diagram of how normals are used in some physics and so on, normals and tangents. And we can see that here, normal, tangent. And again, this represents the force that is keeping the bicycle on the track. Okay, so let's tell me something about this. What do you notice about these two lines? Okay, they're parallel, of course. And parallel lines, here's that equation, here's this equation. What do you notice? Well, you should know that parallel lines always have the same slope, and we can see here the slope is 3, and here also the slope is 3. Great. So slope is 3 over 1 or 3, and here also 3 over 1 or 3. Alright, now these are perpendicular lines. Look at the slopes. Here's the slope of this one. negative 1/3. Here is the slope of this one. What's the relationship between the slopes here? Okay, the slopes of normal lines have a negative reciprocal relationship. That means one slope is the negative reciprocal of the other. Reciprocal means flip the fraction over. Negative means you apply a negative sign. That's an important thing to know as we move forward. So here we have a parabola. Negative x squared plus 4x. There's the parabola. Let's say we were asked to find the slope of the tangent. Well, what tangent are we talking about? Well, let's say talk about the tangent at this point. So let's say that is an x value of 1, and we can see that here. Here's 2, here's 0, and here's a 1. So at x equals 1, here's a tangent line. So how do you find the slope? Well, we know we have to begin by finding the derivative, which is this. Take a close look. And then once we have the derivative, we just put the x value in it, because the derivative function tells us the slope anywhere. But we're saying we don't want the slope at some other point. We want the slope at x equals 1. So we put 1 in here. And when 1 goes in there, we get the slope, and it is 2. So the slope of the tangent is 2. Okay, great. That's what we know already. Next, let's say the next question was find the equation of the tangent line. Well, we just looked at that, so let's try this again to make sure we got it. Okay, so far we have the slope of the tangent. There's the tangent. We have the slope already. How do we find the equation? Well, to find the equation of a line, because the tangent is a line, we need the slope and the point. So how do you find the point? Well, the point is found by saying, well, I know the x value is 1. We already confirmed that last slide. Now, how do we find the y value? To find the y value, you put the point into the original equation. Okay, so we're putting 1 into the original here, and we find out the y value is 3. So when x is 1, y is 3. That's our point, 1, 3. Now we have the slope and a point. We can find the equation of the tangent by using y equals mx plus c, our linear equation. Put the y value here, x here, and we put the slope in as well. So here's the y, 3, here's the x, 1, and here's the slope, 2. C equals 1. Therefore, our equation of that tangent line is 2x plus 1. Okay, great. Let's take this a step forward. So now we have this point established, 1, 3 right here. And let's say now we said, how can we find the slope of the normal? Okay, so we already have the slope of the tangent. The slope of the tangent, oh, and here's the normal, by the way, right? Here's the tangent line, here's the normal line. Slope of the tangent is 2. So what's the slope of the normal? Well, just a moment ago we looked at that. We said, hey, these are perpendicular, and perpendicular lines have a relationship where the slope is a negative reciprocal. So if the slope of the tangent is 2, the slope of the normal, therefore, normal must be negative 1 over 2. Great, now we know the slope. Okay, so we're back to where we started. We have a line, this red line. We know the slope of it. We want to find the equation of it. But to find the equation of any line, we need the slope and a point. Oh, and we have a point because it's the same point we used for the tangent, right? So let's do it. How are we going to find the equation of the normal? We have the normal slope and we have the point which we discovered before. So go ahead, use y equals mx plus c. Let's see what you got. So I put the 3 in here, I put the 1 in here for x, and I put the slope of the normal here. Okay, let's solve for c, and you get 3.5. Therefore, the equation of the normal line is this. Double check your work carefully. Let's keep going. So now here's a question for you to try. We have this equation, and we want to find the derivative of the function at x equals 1. So you're going to find the derivative, put 1 in there, and find that. Then find the equation of the tangent at x equals 1, so we're using that same point, and then the equation of the normal at that point. So let's see, without any steps shown to you, if you can figure this out. Give it a try. And now let's check your work. So here's all that. Check it carefully. There's the equation of the tangent, and then the equation of the normal as well. Excellent. Try another one. You can do it. Find the equation of the normal of this function at x equals 1. Nice. Check your work carefully. Pause if you need to, because I'm going to move quickly. At this point, you should be getting the hang of it. And let's end with a challenge. This one's challenging. It's going to be great. let's get into it. Okay, so I think it's time we end with something just a little more challenging. It's not super challenging, but it's just a little bit of out-of-the-box thinking on this one, so let's try it out. So here's the problem. It says the gradient of the normal to the curve with the equation f of x equals kx cubed minus 2x plus 1 at the point 1b is negative 1/4. So the gradient of the normal is negative 1/4 at this point. Find the values of k and b. Okay, this one is way more abstract. We have a unknown value b here, unknown value k, that's our goal. Try it out, and then I'll help you through it step by step. See if you can get k and b first. Okay, now let's break it down. So first of all, we are told the slope of the normal, the gradient of the normal, the slope is negative 1/4. Great. How does that help us? Well, we know when we have a function and we find the derivative of it, that gives us the slope of the tangent. So why don't we take the slope of the normal and write our slope of the tangent? What is it? Okay, the slope of the tangent must be 4. It's the negative reciprocal of that. Okay, great. There's a start. So now we have 4. Okay, so the slope of the tangent is 4. Now, we know the slope of the tangent can be given to us by the derivative of this function. So how about finding the derivative of that? What is it? Okay, so the slope of the tangent is the derivative of the function, and the derivative is this. By the power rule, we drop the 3, that exponent, in front, so we have 3k x squared, that is reduced by 1, x squared, and then minus 2, the derivative of 2x is 2, so minus 2. Okay, great. So now we have that. And we know that the tangent slope is 4, but that the slope is always different, right, at every point. So we're like, okay, the tangent slope is 4, but at what point? Oh, at this point, 1b. So that means when we put 1 in here, the result of this should be 4. So that means set this whole equation equal to 4, but put 1 in for x. And we get, when x equals 1, we know the slope is of the tangent, the tangent value is 4, so we have that. So we set the derivative equal to 4, and we put a 1 in for x. This allows us to solve for k. So we're going to find one of those two variables we're trying to solve, so find k. Alright, that, and then k equals 2. Excellent. Now that we have k equals 2, we can it can help us find the point b. That's the next one we want to find. So now we know that our original function, we can rewrite it and we can replace this k with 2. That's going to make things easier. Alright, so I think that's what I did next. Yeah, I did it right here. Original function with a 2 in there. And now we have this function which has no variable other than x. So it's like a normal looking function now, and we want to find out what b is. Well, we know that if we put x value of 1 into this function, the result is a y value, and that y value is b. So we can solve for b, right? So b replaces f of x here, but that occurs when x is 1. So x became 1 here and here. So what is b? b is 1. Okay, so like I said, not super tough in the end. I mean, there's not that many steps here, but it's more the out-of-the-box kind of abstract thinking that's necessary that makes this a tougher problem. So a great one to finish with. We will see you soon. Thank you for joining me for this lesson.